Hey everyone, my name is Matt Liam and I'm a Senior Big Data Architect on the Amazon EMR team. This session is going to be focused on how you can take your big data analytics and run them faster, more reliably, and at a lower cost using Amazon EMR. Now I know typically improving on all three of these things at the same time is really difficult. If you want more performance, you usually have to throw more money at it. Or if you're trying to save costs, you have to sacrifice a little bit of reliability. So what we're going to do here today to show you how all three of these things can be achieved at the same time with Amazon EMR is walk you through a cost and performance optimization exercise. We're going to first take a look at a sample workload and cluster and look at the cost it takes to run this cluster across different environments. This is going to form our cost baseline that we're going to compare everything against. We're then going to dig into all the different optimizations and features that are available within Amazon EMR that allow you to reduce your costs. And then we're going to put the two together. We're going to take those optimizations and features and apply them to our cost calculation for our cluster so we can see the exact dollar impact and cost savings that each of these different features and optimizations have on our cluster. By doing this, we'll be able to see how you can take a big data workload and run it faster, more reliably, and at a lower cost. Now, if you're already using Amazon EMR, then by going through this example, it'll give you a good sense of all the different features available. Some you may already be using, some may be new to you, but also very beneficial is sort of the approach that we're going to take and how you can then apply these same optimizations to your existing workloads and cluster. And if you're new to EMR or sort of just getting started, then you'll know what features to take advantage of from the get-go and all the advantages of running big data workloads on Amazon EMR. So with that, let's get started. I wanted to first just spend a little bit of time going over the cost of running big data workloads in the cloud. And it's actually very simple. The cost of running any workload is going to be your unit price, usually measured in dollars per hour or dollars per second, times your usage, how long you're running that service. And so in the case of a Hadoop cluster, your price is going to be dependent on your hardware selection or the infrastructure you're using, and your usage is going to be dependent on the size of your Hadoop cluster or how many nodes you're running. Now, if we're looking to optimize on cost or improve the performance, the big question becomes, how do we reduce these two cost factors, price and usage? Now, on the price side, this is pretty straightforward. If we can get the same hardware or the same compute, but for a discounted rate, either through the spot market or through savings plan, we can reduce costs that way. With usage, there's a few more factors involved here that we have to consider. We can't just stop our ETL jobs halfway through the night and expect nobody to notice. We have to be able to run the same workload, produce the same results, but with less. And one of the best ways to do that is with better performance. Better performance means less usage, which in turn results in lower costs. Let's take a look at an example here. Say, for example, we have a 10-node cluster, and this 10-node cluster runs for 10 hours, and it costs $100 to run. We also have a second cluster. This second cluster is the same size as our first cluster, 10 nodes, but it runs twice as fast. Say, for example, it's running the latest version of an application, or we've done some tuning or optimization, but what this 2x performance allows us to do is run the same workload as the first cluster, but in half the amount of time. And now, since we're only running the cluster for 5 hours, our cost also goes down from $100 to $50. And so this is why performance is so important. Better performance means you can complete the same workload, but with less resources, resulting in lower costs. Another way of reducing usage and in turn resulting in lower costs is with higher utilization. This can be achieved through right-sizing your instances or using auto-scaling, but essentially the closer you're able to match the compute resources that you're paying for with your actual cluster workload pattern, the lower your costs will be. Take this graph, for example. The orange line represents a typical workload pattern on a cluster. You have an initial peak in the beginning, and then it drops to close to 0 in the middle, and then you have some jobs that trickle in near the end. The purple dotted line represents a cluster without auto-scaling. So in this case, the cluster cost here is fixed, independent of what's actually happening on the cluster. And so the black space in between the purple dotted line and the orange represents resources that you're paying for, but your cluster or job does not actually need. And so the whole goal with auto scaling is to minimize that space as much as possible. And that's what we see with the blue line. With the blue line, your costs or the resources that you're paying for is a function of the load on the cluster, which results in significant cost savings. And so that's why higher utilization equals lower costs. The reason I wanted to cover these two concepts is because a lot of the features and optimizations that we'll be covering in this talk focus around these two areas, performance and utilization. So with that covered, let's take a look at our example cluster costs. For this calculation, our requirement is a 21 node cluster that's running 24/7. So our usage is going to be 15,330 hours. We get that number by taking 21 nodes, multiplying it by 24/7, and then around 30 to 31 days per month. The compute requirements are M5 4X large, or the equivalent of CPU and memory. And we're assuming that we use an EMR version greater than EMR 516 because that's where all the features and optimizations exist. Our storage requirements are 10 terabyte of unreplicated data. So if we factor in HDFS, or if that's where we're going to store the data, we have to factor in the 3x replication factor. And so when we take those requirements and translate them to costs across different environments, in our on-prem environment, we estimate that cost to be around $6,000, which is a rough ballpark number. With our Hadoop on EC2, this is our self-managed Hadoop offering. Your cost is going to be around $14,773. The bulk of that cost is coming from the compute section, where we've taken the usage, the instance hours, and multiplied it by the unit price of M5 4X large instances. The storage cost is going to be $3,000. This is taking the 10 terabytes, multiplying it by the replication factor, and then factoring in the cost of EBS. And then now finally, with our optimized EMR pricing, we're actually starting at the end here and then going to work backwards. So this cost, $2,149, is the cost we can achieve with all the different optimizations and features. We're able to lower the usage, how many hours it takes to run our workload, as well as the unit price, how much we're paying per hour to get to our optimized EMR pricing. So let's see how we got there. We're going to start with EMR's optimized runtime for Apache Spark. Remember, better performance equals less cost. And when we compared EMR 5.30.1, which includes the optimized runtime, with EMR 516 that does not have the runtime, we see an almost 4.1x improvement in performance. We also looked at costs. And when we compared the cost of EMR with some of the third-party managed Spark offerings, including their runtime, EMR is 1/10 of the cost. We're making improvements across all areas, including the default configurations of Spark, query planning and optimization, as well as the job execution. The best part of all of this is that the Spark runtime is turned on by default starting in EMR 5.28 and is 100% compliant with Apache Spark APIs. That means there's no change required to your code, the APIs you're using, or how you're actually submitting these Spark jobs. Next, let's talk about auto-scaling. So we previously talked about how higher utilization equals lower costs. And with EMR's managed scaling, it'll automatically resize your cluster for the best performance at the lowest cost possible. Some of the key features of managed scaling is that it is extremely responsive. It uses a lot of data points, a lot more than before, to determine when to scale up and when to scale down, and can react to changes in your workload every 5 to 10 seconds. We've also expanded the support for managed scaling to be able to auto-scale on not just instance groups, but instance fleets as well. When we talk to customers and based off our own tests, we see cost savings of anywhere between 20 to 60% depending on your workload pattern. Let's take a look at an example of managed scaling. So this here is a graph of a CloudWatch metrics graph that shows a job being submitted to a cluster at 3 different intervals approximately 30 minutes apart. The blue line represents the load on the cluster through the metric container pending ratio. When you initially submit a job to a cluster, you're going to have a really high container pending ratio because these containers have not yet been assigned to executors or tasks to be run on. The important thing here with autoscaling is how fast does your infrastructure react to jobs running on the cluster? And this is represented by the purple line, core's requested CPU, which is essentially EMR acknowledging that it needs more resources and is going to go to EC2 to get that capacity. This happens almost immediately after the blue line starts to increase. The orange line represents the requested resources actually running on the cluster, and this happens shortly after the job is submitted. We see similar behavior on the downscaling side. Once the load on the cluster drops to 0, represented by the blue line going to 0, EMR detects this right away and starts downscaling of the cluster. We see the nodes being terminated when the orange line also drops to 0. Fast reaction to your workload is really important because you don't want to pay for any resources that your cluster or your job doesn't actually need. All right, so we've talked about some of this application optimizations with Spark runtime. We've talked about managed scaling to improve utilization. Let's look at some of the hardware optimizations that are available within EMR. With EMR, you're able to use AWS Graviton 2, which provides a really big leap in terms of capabilities and performance compared to first generation Graviton, as well as instances within its own family. We did some benchmarking where we compared M5 instances versus M6G instances, both using EMR 5.30.1 with a TPC-DS benchmark with data stored in S3. What we found was there was a 12 to 16% difference in performance when we compared M6G instances versus M5. And if you took those same instances and looked at the cost, M6G instances are 20% lower in cost versus the same sized instances in the M5 family. When you put those two things together and you take a workload and you run it on an M5 cluster and you take that same workload and you run it on an M6G cluster, what you're going to find is that the total cost of running that job or that cluster is going to be 30% lower on M6G instances. Similarly to the Spark optimizations, it requires absolutely no change in your application, workflow, or provisioning. You just need to select these latest instances when provisioning your cluster. All right, next let's talk about Spot. So Spot instances are unused EC2 capacity that use the same infrastructure as on-demand, but are 70 to 90% off the cost. The Spot pricing is very predictable. It's set by EC2 and adjusts gradually based off long-term trends of supply and demand for that specific instance and capacity. When it comes to interruptions can happen, but you can configure EMR so you're only interrupted when on-demand needs capacity and not for other reasons like your bid price was too low, for example. And despite interruptions potentially happening, Spot still makes a really great fit for big data workloads because of their fault-tolerant nature. To help reduce Spot interruptions, EMR now also has the ability to select up to 15 instances within a single instance fleet. This is really important because EMR uses real-time EC2 information to determine which instances within your fleet it should use to provision your cluster from a cost perspective, as well as which instance is least likely to be interrupted. So say, for example, you're going to provision a cluster, and within your fleet, you've specified C5 instances and M5 instances. Now, for whatever reason, M5 instances are really popular at this time. The demand is really high and the Spot capacity pool is really low. So your chances of interruptions here are really high. EMR knows this and won't provision that type of instance, but will provision the C5 instances instead. So Spot is great, right? It provides a really big opportunity for you to reduce your costs, but you have to know when to use Spot. I've summarized it here. Essentially, it comes down to if you are running a long-running cluster or a critical workload where you need reliability and predictability in your job times and performance, then don't use Spot for any type of nodes where if they were to go down or you can't get that capacity, it's going to impact your job runtime or your cluster. So in this case, it's going to be master nodes and core nodes. If a master node were to terminate, you'd have to reprovision that cluster and rerun your job. Similarly to core nodes, if a core node were to be interrupted, this would cause a HDFS rebalancing. And if you lose enough core nodes below your configured HDFS replication factor, your cluster would go into an unhealthy state. With task nodes, Spot is still a great fit even if your workload is really critical, because in the worst case scenario, the job or the task that was running on that node would just be reassigned to another node within your cluster. Now, for cost-driven workloads or application testing, Spot is a great fit for all different node types because you can always just rerun your job or reprovision your cluster if a Spot interruption were to happen. Now, one common pattern that we see with a lot of customers who are using Spot is mixing on-demand and Spot within the same cluster. Say, for example, you have a really critical workload that has a 5-hour SLA that you cannot miss. What you would do here is you'd provision enough on-demand capacity to meet your 5-hour SLA, and then use Spot instances to lower your costs and potentially improve your runtime. In the worst case scenario where you don't get that Spot capacity, you still have your on-demand instances to fall back on so that you can still meet your SLA. In the best case scenario, or the scenarios you actually do get that Spot capacity, you now have additional compute that would bring down your cluster runtime, and now your total cost of your cluster becomes a blended rate between the on-demand price and the Spot price. So your total cost of that workload will also go down. Let's take a look at an example that demonstrates this. So again, we have our 10 node cluster. It runs for 10 hours like last time, and it costs $100 to run. This time though, we have a Spot cluster. These Spot nodes are 50% of the on-demand cost, which is definitely on the conservative side. We typically see anywhere between 70 to 90%, but for simple math, I chose 50%. Now, the runtimes are going to be the same. Remember, Spot infrastructure is the same as on-demand, so we don't expect any change there. The big change is going to be in the cost of the cluster. The cost of the cluster is going to go down from $100 to $50 because of the 50% off the on-demand nodes, which is great, but the risk here is that because our whole cluster is Spot nodes, there is a chance that that cluster runtime of 10 hours may slip, and there's no guarantee that we're going to always run for 10 hours. So what do we do here? We mix on-demand and Spot nodes into the same cluster to get the best of both worlds. So this is our third cluster here. This third cluster is 20 nodes, half on-demand, half Spot. And two things are going to happen here. First, the total runtime of our job is going to go down from 10 hours to 5 hours, assuming that performance is linear, because we've essentially doubled the compute from 10 nodes to 20 nodes. And secondly, our cost is also going to go down from $100 to $75. Now, it's not as much as our cluster with all Spot, but the benefit here is that we get reliability. Because again, in the scenario that all Spot nodes are depleted and we don't get any capacity, we can still use those 10 on-demand nodes to meet our SLA and get that 10-hour runtime. So when it comes to lowering costs with Spot, the key things are to remember is one, use instance fleets to reduce your interruption rates, choose the right purchase option so that depending on your use case, and three, mix on-demand and Spot to reduce your runtime as well as improve your total workload costs. Okay, let's now move on to storage. With EMR, you can use Amazon S3 as your persistent data store to lower costs. S3 provides you the ability to decouple your compute and storage, which essentially allows you to grow your storage infinitely independent of your compute at S3 storage rates, which is 2.3 cents a gigabyte a month, or $280 a terabyte a year, which is a much lower cost than what you can achieve with 3x replicated data sitting in HDFS. The other benefit of S3 is that you can point many clusters to the same source of truth. So say, for example, you have different departments that all want to operate differently. They can do so and act in isolation in parallel with your core production workload. This also means you can run interactive query workloads with ETL type workloads, and it provides you a lot more flexibility in how you choose to operate. Another benefit is that you can evolve your analytical infrastructure very easily. Say there's some new open source tool that you want to try out, you can provision another EMR cluster with that technology in parallel with your core production workload. Once you've experimented and decided which tech to adopt, you can cut over from one EMR cluster to another. And so this provides you a lot of future proofing and option value, because as your analytical toolset evolves, your infrastructure can evolve with it without any expensive replatforming or retransformation of your data. As we all know, S3 also provides 11 nines of durability, and you don't need to re-replicate your data once it's there. Now, EMR still has HDFS, and it still has a place. There are some use cases where HDFS is a great fit for iterative reads on the same data set or disk I/O intensive workloads. Now, if you're concerned with the performance of S3, you shouldn't be. We did some benchmarking where we compared HDFS and S3 and found that S3 is slower by only 8%. And when you factor in the cost difference between HDFS and S3, as we'll see on the next slide, it often makes up for that difference. Taking our 10 terabyte requirement, for example, the cost of storing that in HDFS on EBS is going to be $3,000. With S3, depending on your access tier, you're going to be able to save anywhere from 90 up to 96%, not only because the S3 storage rates are significantly lower, but our requirement for how much data we need to store goes down from 30 terabytes to 10 terabytes because of we don't need to factor in the replication factor. All right, so now that we have a better understanding of all the different optimizations and features that allow us to reduce our costs, let's apply them to our initial requirements to see how we got to our optimized EMR pricing. If you remember from the beginning, we had an initial usage hours of 15,330 hours. This is the amount of hours required to run our workload. Our unit price was $0.768, which was the price of our M5 4x large instances. And so now let's go through all the different optimizations. Starting with our Spark performance. With Spark performance, we see an improvement of anywhere between 3.1 to 4.1x improvement in performance. Taking the more conservative number, what that means is that if we use the EMR Spark runtime, we can run the same workload in approximately 5,000 hours versus the 15,000. So this reduces the amount of usage or those instance hours to the 5,000. With managed scaling, we see anywhere between 20 to 60% improvement in performance, in cost of your cluster through higher utilization. And so factoring that into our usage, it brings down our instance hours further from 5,000 to approximately 4,000. With spot instances, we're using M6G instances, and the spot price is 72% lower compared to on-demand. This gives us a new EC2 price of $0.1676 per hour for our task nodes. I specifically mentioned task nodes here because we're going to assume that this cluster runs a critical workload, and we're going to do half spot nodes and half on-demand nodes for this cluster, where the spot nodes will be task nodes and the more critical nodes like our master and core will be on-demand. So we're going to have separate pricing for those. With Graviton 2, we get two benefits. We get 20% lower costs, which reduces our EC2 price to 0.616, and this is going to be for our master and core nodes. And we also get 14% improvement in performance, which is going to have similar impacts as our Spark performance, where it reduces our instance hours from around 4,000 to 3,402. With storage, HDFS versus S3, we get 92.5% savings versus EBS with 3x replicated data. And so this gives us a new storage cost at S3 rates of 2.3 cents gigabyte per month, as well as it reduces our storage requirements from 30 terabytes to 10 terabytes. And so when we put all of this together, on the compute side of things, we have a new running instance hours of 3,402 hours with all the different optimizations and features. And so when going through these costs for EMR, it's just going to be the cost or the unit price of EMR for M6G instances 4x large times the 3,402 hours. With EC2, again, we are splitting it up between half on-demand and half spot. So we're taking the respective cost for each and multiplying it by half our required instance hours. For storage, we're taking the S3 storage rates, multiplying it by our 10 terabyte data requirement, and we still leave some space for HDFS, but since the majority of our data is going to be stored in S3, that price becomes almost negligible. And so finally, when we sum everything together, we get our optimized EMR runtime of $2,149, which is down from close to $18,000 without any of the optimizations. We get significant cost savings across EMR, EC2, as well as storage. Probably the best part of all of this, in addition to the cost savings and better performance, is how easy it is to take advantage of all these different features and optimizations. All you have to do is upgrade to the latest EMR version. There's no change required in your application code or how you submit the job. A lot of these features are either turned on by default or something you need to simply configure or select when provisioning your EMR cluster. This is why it's also really important to stay up to date with the latest EMR version, or always try to upgrade as much as you can, because with every EMR release, you can expect similar optimizations and features that will help you reduce costs and improve performance. Which is not everything. On top of providing the lowest cost and the best performance, EMR provides the latest and greatest in open source technologies and their versions. It's fully secure, providing the abilities to configure encryption, authentication, as well as network security. And it's also very flexible. If you want to run custom AMIs or if you want to install your own monitoring scripts, you can do so. And lastly, it's simple and easy to use. All you need to do is specify your EMR version, the applications you want to install, and the hardware compute requirements, and EMR will take care of the rest. And so to recap, let's go back to our initial cost formula that we talked about in the beginning. And the question that we were trying to answer back then is, how do we reduce these two cost factors, right? If these are the two factors that affect the cost of running big data workloads in the cloud, what can we do to bring these down? And it's actually really simple with EMR. On the price side of things, use spot instances. You get 70 to 90% off the cost, and as long as you're using instance fleets or using a mix of on-demand and spot, you can still get the same level of reliability. Keep your data in S3. Not only are S3 storage rates significantly lower, but you don't need to re-replicate your data once it's there. With Graviton 2, you get automatic cost savings of 20% versus the same size instances in the M5 family. And then on the usage side of things, this was all about how you can run the same workload, produce the same results, but with less. And this is where performance and higher utilization plays a big factor. For our optimized runtime for Apache Spark, you can see performance improvements of anywhere between 3.1 to 4.1x. With Graviton 2, it shows up here again because not only does it provide lower costs, but the hardware capabilities allows you to run your applications anywhere between 12 to 16% better. And finally, use managed scaling to avoid paying for resources that your job or cluster does not actually need, allowing you to save anywhere between 20 to 60% depending on your workload. And so when you put all these things together to run your big data analytics on Amazon EMR, you're able to get faster performance, lower costs, and reliability all at once. And so with that, I just want to say thank you so much for your time. I hope you enjoyed this session and found this information useful. Thank you.